In the last video, I talked about how to find an inverse function and the basic idea, but I wanted to just talk about a few more properties of inverse functions, and we'll keep talking about this in class this week. But one of the points about an inverse function, it's always the opposite of the original form. Like if I have a function 4x plus 5 and I find its inverse, the whole point of that inverse function is to be like exactly the opposite, to undo the function or reverse whatever the first one did. Kind of like with the World Series example, the regular function would be, well, in what year, or in this year, who won the World Series? The inverse function would be, well, what year did this team win the World Series? It's going to be the reverse question or the reverse correlation between those things. And in that case, it wasn't possible because it wasn't one-to-one. But you know, the whole idea of undoing the original is kind of a powerful idea, and that's kind of the whole point. And what I wanted to do is look back at the example we just were working on and see how an inverse function properly undoes the original function. But also, I've kind of forgot to talk about this, but we always let f to the minus 1 power stand for the inverse function. That's just the notation we use for a function inverse. And this is a little bit of a strange notation because it kind of, like, usually in math, when we write something like x to the minus 1, that means reciprocal. It means, you know, I'm going to take 1 over x and divide by x to the first power. Because negative exponents, that's just what they mean in math, is instead of multiplying, they mean dividing. But with function notation, I just wanted to mention that this is not equivalent to 1 over f algebraically speaking. So the minus 1 power, it's not an algebraic notation for this function, which is really confusing because a lot of times we use something like f squared to mean literally f squared, f to the second power. But basically, f to the minus 1 does not mean 1 divided by f. And you might be thinking to yourself, well, why? And this is just a poor, it's something that's existed as a mathematical notation for hundreds of years, but it's not good notation because usually, algebraically speaking, minus 1 power means division. And that is still true, but I just want basically delete that from your mind when you're thinking about f to the minus 1. Just what you can remember is f to the minus 1 stands for an inverse. There is a reason why we write it this way. It's because that typically when you have 1 over f, if this were an algebraic expression, 1 over f times f, if you were thinking about them as multiplication, would make 1, and it would form a cancellation. And inverse functions do form a cancellation on the function level, which is why it sort of makes sense. But I just wanted to, you know, really emphasize this does not mean 1 over f. It means function inverse. And the same thing goes for like trigonometric functions like sine over x. And if we were thinking about what does sine to the minus 1 of x mean, that stands for a sine inverse function. It doesn't mean 1 over sine. 1 over sine is actually equal to what's called the cosecant function, which is something different entirely. But it's a notation thing. It's really important, and I just wanted to make sure that was quite clear. But also, actually, before we go back and do another example, I wanted to return back to the function machine, which is where if we have a function like, I don't know what's going on with my slides here. They're being weird. But, you know, the idea, you know, we can think about a function as a machine where we put in x, we do some math to it, and what we get is f of x by some formula, the output, domain, and range. But the whole idea behind an inverse function is, let's say I knew the answer and I wanted to know what was the cause, what input value correlated to that. That's exactly why the inverse function is important and relevant. Because if I were to calculate an inverse function, again, which we use f to the minus 1 to represent, and if I plug in the output, the range from that, what it should do is get me right back to the input and figure out exactly what I started with. So let's look at the example we found in the last video, and hopefully, you know, I can be a little bit more clear about what I'm talking about. But in the last video, we took this linear function, we found its inverse, which is actually still linear. But basically, let's say we were to plug in, I don't know, f of 1 into the original function. Well, that'd be 4 times 1 plus 5, which would be 9. Cool. And again, what I have is, you know, in a function, there's always a set of correspondents. I could imagine this as an arrow diagram. Well, 1 has an arrow drawn to 9. And again, this, since it's a line, it would be 1-to-1. You want to make sure it's a 1-to-1 function before you do all this. But, you know, we can tell that it had an inverse just from the algebra. But, okay, so what's the point of an inverse? But again, kind of getting back to the basic point of an inverse is that it should undo exactly what happened, because we had the correlation between x and y. An inverse function should reverse that, and if I plug 9 into it, it should take me back to 1. That is the point. And so what we could do is check our inverse to see if that actually happens. If I plug in 9 into my inverse function, that should take me back to 1. So let's do it. If I plug in 9, I would get 9 minus 5 divided by 4. Well, 9 minus 5 is, of course, 4. 4 over 4 is 1. And wow, it works. And again, that's kind of the point, is it's not amazing. It's not a coincidence. That is exactly why we care about inverse functions, is we can reverse the correlation, and my new function will exactly undo what I had before. And this is very useful for back solving, or if you just wanted to reverse a process, like in say for example, you're interested in computer programming. If you design a functional program and you wanted to reverse engineer it and undo something for whatever reason, that you could think of that as like what an inverse function is. And you know, depending on the level of complexity of a code, it might be possible, it might not be. And you could draw some parallels to whether a mathematical function is 1-to-1 or not. Anyways, let's do one more example of finding the inverse. And again, this is like not a necessary thing, but you know, I just wanted to show you what the purpose of an inverse function is, and we kind of verify that it's working the way it should be. And this should work no matter what you plug in. Any number you plug in, you should be able to reverse it, assuming it is the proper inverse. So let's check, and also it's, you know, what it also says to do in the packet for this week is find the domain and range of each. But with those two, they were both all real numbers, because each one was a linear function. And, you know, when you switch the domain of a linear function, all real numbers, both of them are the same, so it's not particularly exciting. But basically, before I do anything, I could make sure it's invertible. But if you recall, the square root of x is an invertible function, and if we do some other stuff to it, it will remain such. But if you weren't sure, you could always start by graphing your function to make sure it is 1-to-1. So let's go ahead and look at a graph of number 2. Number 2 is indeed 1-to-1 because, you know, it has that, again, it's got the shape of a half parabola. And there is no repeating when it comes to square roots. So step 1, check. Step 2, we want to change it to y and invert them. So what I would probably do is just write this as x and change this to y, kind of do step 2 in one single step. But basically this guy will become a y, and I'm going to switch the location of x and y. And step 3 is to then solve for y, because when I'm swapping x and y, that is the essence of inverting it. And then when I'm solving for y, I'm writing it as a function. So I would want to subtract 3 to the other side. I could square both sides. And remember that if you're squaring both sides of an equation, you want to make sure to properly FOIL in the case when it does need to be, because this would not just be x squared minus 9. I would need to get, well, it would really be x squared minus 6x plus 9 because of FOIL. And I would also need to divide by 2. So I would get y is equal to x squared over 2 minus 3x plus 9/2. Or you could have just left it factored divided by 2 if you prefer, which might just be cleaner to leave it like this, x minus 3 squared all over 2. But again, they're all just different ways of writing the same answer, whatever. Because this way is actually factored, and we can tell the zeros in that form. And again, last step would be to write it as f inverse using the inverse function notation. And there we have it. Cool. But one thing I wanted to mention is that sometimes, like looking at this answer, since this since the inverse function here is a polynomial, actually we would think that the domain of this function would actually be all real numbers. And in a vacuum with no other information, that would be perfectly true and sensible. But it kind of coming back to the original function, the domain of the original function was 0 to infinity. Because in a square root, if you plug in a negative, you get imaginary answers, you get non-real answers. And when we're talking about domain and range, we're always talking about the real values in the graph, not the imaginary values. So to keep it real, we would need to only use values from 0 to infinity. And the range, just from looking at the graph of that function, would actually be from 3 to infinity. Usually a square root function is from 0 to infinity, but because we added 3, it caused it to vertically transform up 3 units and shifted the range up to 3 as well. But kind of the reason why I'm getting at this is for an inverse function, it always has to have the reverse domain and range. So if I was talking about, well, what is the range of the, this would be for f, and if we're talking about f inverse, the domain should be the range of the original function, and the range of the domain of the original function should become the range. Basically, domain and range always have to be flip-flopped in inverse functions. And if we're thinking about this, well, technically the generic domain of this function is not that. But because it's correlated as an inverse function, it has to have what we call a restricted domain. It's not the full story. Because again, the whole point of an inverse function is that inputs and outputs are reversed. And that would imply that the domain and range is also reversed. So basically, even though in this you're allowed to plug in 0 or -5, it works mathematically speaking, since it would not be correlated back to the original point. It would not be part of the inverse function's domain because it's not just a function in a vacuum. It is related back to the original function.